Welcome to ECE 320A, a review session for exam number 2. We're in a slightly different location, but hopefully everything will go according to plan. At least for those that are here, I think you'll be able to follow along. We'll see if it works for those that are trying to watch this on a recorded basis. Just to make sure we're all on the same page, the material that you will be expected to know for exam 2 is chapter 12 material, and it's really all of chapter 12. Homework assignments 3, 4, and 5 will be that's what you're expected to know for exam number 2. And that involves this list, which I haven't posted in any other form yet on D2L or otherwise, but essentially you should be able to follow the chapter 12 material that's on the practice exams. There's more material on those practice exams than just chapter 12. We won't be expecting you to know power, which is chapter 11 material, and there may be some S-domain equivalent circuit problems that you don't have to know. That's chapter 13 material. So just try to make sure that you're comfortable with what I'm meaning when I say chapter 12, and if you go to the textbook, you should be able to follow what we're doing. Essentially, it's Laplace transforms, inverse Laplace transforms, being able to write what I call the governing differential equations for a circuit, an electric circuit. Those are the integral differential equations for a RLC circuit. And you need to be able to establish the initial conditions on capacitors and inductors, and essentially if you are given some circuit that maybe a switch is in one location before t equals 0, you're essentially doing a final value problem up to t equals 0 minus. From t equal minus infinity, you're looking to see the circuit is now in steady state, and what are my inductor values or currents, and what are my capacitor voltages. Then if the switch is thrown, that's what your circuit looks like for non-negative values of time with the appropriate initial conditions that you just found before the switch was thrown. And we'll try to work a problem, and hopefully that will become a little bit more clear. I may ask you, I probably will, about the structure of a solution. So I might give you a differential equation and ask you what's going to be the solution structure to that differential equation. Sometimes you don't even really need to worry about the initial conditions. The initial conditions really just influence the numerator expression, and consequently that doesn't determine the structure of your solution. If you're given different inputs, though, then you need to make sure that you're applying the Laplace transform to the appropriate inputs. And maybe we'll go through an example on that also. With respect to performing the Laplace transform or the inverse Laplace transform, you should be able to convert the expression into something that's recognizable from your table, and you may have to use the other table of what's called the operational transforms. What if you have a mismatch between the delay and when you switch it on, for example, in your system, or some argument that's now being turned on at a funny time with a unit step function that may not be turning on at 0? Can you make the arguments look the same? And that might just now introduce a particular scaling expression, and we'll try to work an example that shows that also. With respect to partial fraction expansion, you need to be able to do both cases with distinct roots and repeated roots, and you need to make sure that before you get too far into it that you've made the numerator polynomial strictly less than the denominator polynomial. You may have to divide the denominator into the numerator 1 or 2 times until you get that numerator of your remainder less than, strictly less than the order of your denominator polynomial. Meaning there may be some improper transfer functions directly or sort of indirectly through a few terms that you're asked to now inverse Laplace transform. That should be clear from some practice exams. You should be able to find poles and zeros of transforms, and you should be able to evaluate or find or use or apply the final value theorem and the initial value theorem, like what we talked about in class today. Are there any questions on the topics that we're requiring you to know? It's really chapter 12 and homeworks 3, 4, and 5, your most recent 3 homeworks. Let's look at an example, and these are, I don't know if these are coming from practice exams or not, but let's say that I ask you, some will and some may not, what is the structure of v of t? And let me say that for, let's say, part A of this example, that v of t is actually governed by a differential equation that's forced by a driving waveform. Suppose that we have 1/2 the first derivative of v plus 4 times v, then minus 5 cosine of 3t, and that forced first order differential equation is true for t greater than or equal to 0. And now you're asked to find, okay, what's the structure of the solution to that differential equation, where the solution is v of t? That's the question. Is it clear what I'm asking for? You don't have to find the complete solution. You could, but that's more work than's needed when I'm just saying find the structure. I'm really wanting you to find the partial fraction expansion form and then write your answer in terms of those partial fraction expansion coefficients and not evaluate for those coefficients. So you're not held accountable for having a particular calculator or not. You all sort of have to do the same steps. Is that clear? How would you approach that problem if I just wanted the structure? Can you already anticipate what that structure is going to be or what it might look like? It's a first order, so now you're going to have a decaying exponential. Maybe we don't yet know what the frequency or the time constant of that decaying exponential will be, and you're being forced by a sinusoid. And anytime you shake a differential equation with a sinusoid, you have the potential of obtaining a cosine at that frequency and a sine at that frequency. And this particular forcing function is not exponentially damped. It's always on. So you're just going to sit there in this steady state position and be shaking at a frequency of 3 radians per second. So if you didn't do anything else, you could say, well, v of t at least has a sine and a cosine term at 3 radians per second if you didn't even consider the differential equation part. Really. Okay? But you might now Laplace transform that, which really means I'm asking you to Laplace transform a derivative, which I'm hoping that everyone will be able to do, and the scaling factor is just going to be there. That's a factor of 1/2. The derivative's Laplace transform is now just s times v of s minus the initial condition on the time domain waveform v of t plus 4 times v of s minus, and now what's the Laplace transform of 5 cosine of 3t? That's the first step in this process of finding the structure. I'm going to go ahead and keep the initial condition in there and show you why it really doesn't matter if you're just interested in the structure. But now you're trying to isolate all the terms that involve this capital V of S, because that, when you inverse Laplace transform, that's the structure that you want. You want the little v of t's time domain waveform. And if I combine those, I now have a 1/2 s plus 4 times v of s. And I then have that equal to, let's say, a 1/2 v of 0 minus plus a 5s over s squared plus 3 squared. Just moving all the terms not associated with capital V of s to the other side. And I don't like that coefficient in front of the s right now. It's making me feel not so warm and fuzzy. So I'm going to just multiply the whole thing through by 2 everywhere, and that'll get rid of that 1/2. Meaning I can convert that to s plus 8, capital V of s, equaling v of 0 minus plus 10s over s squared plus 3 squared. Is that okay? And now I know where my real pole is going to be living, because now I just solve for capital V of s. V of s, I divide by the polynomial scaling capital V of s. V of s now becomes v of 0 minus over s plus 8 plus 10s over s plus 8 s squared plus 3 squared. Questions on that? Is everybody comfortable with where that came from? And now you can really write down, I hope, by inspection, the structure of little v of t. You could put these two terms over a common denominator, but this one is going to give you what kind of an expression in the time domain? An exponential, and what's going to be in that exponential. So when I ask for the structure, I want you to give me that exponential. I don't need you to give me the coefficient in front of it, but I do want the exponential terms and the frequencies in the cosines. So it will be e to the minus 8t. Everybody comfortable with that? So I would probably, if I had to do this all the way through, I would find, maybe I would inverse Laplace transform this piece, and then I would inverse Laplace transform this piece instead of combining them and then finding the inverse. That's just more algebra. So I'd maybe just leave it separated and find the two different inverse Laplace transforms, because that's a linear operation, and then I can add them at the end if I want to. So this first term on the right gives me an e to the minus 8t. And what terms does this second term give me? It gives me a cosine and a sine based on this s squared plus 3 squared, but it also gives me an e to the minus 8t again. So I have two of those, and if at the end I wanted to combine them, I could. But if I'm just asking for the structure, I now know what three terms I have. I have one that's e to the minus 8t, and I have a sine and a cosine at what frequency? 3 radians per second. And that's my structure. Meaning now I can write, really, just based on this and that discussion that I just had, that was my thought process that I would be doing on the exam. I would say, okay, therefore, v of t is now going to be just some a, e to the minus 8t, plus a b cosine of 3t plus a c sine of 3t for non-negative values of time. Is that okay? Or if you wanted to, and it would be a correct answer, you could say, I would like to just write that as a e to the minus 8t plus some b bar cosine of 3t plus an angle theta. And that's equivalent. That's fine. That also would be an acceptable structure for the answer. What I'm after in your structure is this, minus 8. I'm interested in that. And if you stick with what's going on in that second example, I need you to have those two pieces. The theta accounts for this sine and cosine. But in these sine and cosines, the important part is this frequency. And in the other term, the important part is that decay rate in the exponential. Are there questions on that? Yes. So now the question was the cosine and the sine terms, when do they need the e to the minus at, and when do they not need that? Is it clear? And obviously it's not quite. So why is this factor, this s squared plus 3 squared, why does that not include the decay? So we need, if you had s, instead of s, you had an s plus a quantity squared, then remember where those roots are? They're in the complex left-hand plane. They have a negative real part. Here, where are your poles? They're right on the imaginary axis. And when you have poles right on the imaginary axis, all you have is an oscillator. It's just continuing to shake. It's not decaying. Because of that, it's missing the e to the minus at piece. Does that help? So this second term in the denominator on the second piece of capital V of s, if it had an s squared plus an alpha s plus some other piece, and if alpha was positive and that other piece was positive, you know immediately that you're present and positive, and you can now figure out what your decay rate and your frequency would be by sort of completing the square or doing the quadratic formula and finding where's my real part and where's my imaginary part. The real part gives you your decay. So if you had a polynomial, so instead of v of s, maybe you ended up with a, let's say, a v bar of s that looked like alpha, no, not, let me not do that. Let me say a bar over s plus 8 plus, and now let me say we have, I don't know, 6s over s plus 8, but now we have s plus 5s plus 15. Is that even going to be what I want? Probably not. Because now I have, bummer, no, not, let me not do that. Let me say 75. Okay? So now what am I doing? Now what I want to do is I want to find where are those roots of s squared, whoops, s squared plus 5s plus 75. If you think of that as, ooh, that's pretty bad too, isn't it? Maybe I want to do the following. I want to be able to divide that by 2 a little cleaner. Maybe I make it that way. Okay, so now I have s plus 5 squared, because that will give me an s squared plus 10s plus 25, and then plus another 50 will get me up to the 75. And now I can rewrite that s squared plus 10s plus 75 as an s plus 5 squared plus, kind of ugly, square root of 50 squared. So a little bit bigger than 7. Is that okay? meaning my poles here in the complex S-plane would be at -5, a little bit bigger than J7. So this is now at -5 plus J square root of 50. And the other one would be down here a little bit more negative than minus J7, and it would be at -5 minus J square root of 50. And the V bar of S would give rise to some A e to the minus 8t plus, and now I could say B bar e to the minus 5t cosine square root of 50t plus some angle theta. So what you're keying in on are those poles in the denominator. And if they're complex, then you need to find how far into the complex S-plane are they with the real part, and that gives me my decay. And then how far up on the imaginary axis are they? That gives me my damped frequency. That gives me the, whoops, scroll up. It gives me my frequency on the cosine. Is that making sense? Is that helping? So really, you look at your denominator and you factor it. And once you have all those poles identified, now you should be able to define what your structure is. You just look at those poles. If you have real poles, and we did have a real pole, we had a pole where? A real pole. In this example, we had a real pole at -8, didn't we? So we could, if I said draw the pole zero diagram for that capital V bar of S expression, you would have these poles. And I wouldn't ask you necessarily to draw the zeros because I didn't want you to locate anything in the numerator. That would be more algebra, and you don't need to do that for the structure. Questions on that? Yes. So now, how do you know if it has a sine and a cosine? If you have an imaginary piece, you have a sine and a cosine. And if you do not have a real part to that imaginary part, then it's purely on the imaginary axis, and you do not have the exponential decay. Or if you had poles over here in the right half plane, what would that exponential piece look like? It has a positive. It's e to the plus 2t or e to the plus 10t, and that's blowing up. So you don't want to design something like that unless you are trying to make something burn up. Because if it's electronic, it's going to go unbounded. It's going to hit whatever limits you have in your circuit pretty quickly and probably burn up. So you don't want roots. And if you have RLC, just purely RLC circuits where your resistors are positive, they're not negative, you shouldn't end up with any roots over here in the right half plane. So if you do, and you're analyzing a circuit, you go, oh, I must have an algebra mistake. And I would write that on my exam. If you end up and you do the quadratic formula and you end up with complex roots with positive real parts in just a pure RLC circuit, I would say I must have an algebra mistake because I have roots in the right half plane, and an RLC circuit should decay with time. It should have some damping. That's what the resistors do. Is that okay? Did that answer your question? So you're going to get sines and cosines if you have an imaginary part to your roots. If you have a real part to those same roots, then you're going to get the e to the minus something in addition to the sine and cosine. So you'll have exponentially decaying sines and cosines. If your poles are purely imaginary, only on the complex axis, then you don't have the decay. And all you're doing is sitting there and shaking at the frequency. The frequency given by the distance you are away from the horizontal line. Is that clear? It's a very important concept and very powerful. Once you kind of get that, it's pretty easy for you to start thinking about what kind of a structure do I have for this circuit? Well, where are your poles? I can tell you what's going to happen relative to the time domain behavior. Now, I could change that. So now you've spent half of your time on part A of problem 1, so you'll want to make sure you're going much quicker on the exam. But I could say part B could be 1/2 dv dt plus 4 v of t minus 4 equals 0 for t greater than or equal to 0. Now I'm really just sort of wanting you to see what's changed or what's different. And maybe it's been too long since there was our original differential equation. That compared to the B differential equation, I've only changed the forcing term, haven't I? What's driving this differential equation? In the previous one, it was a pure cosine, and that's going to cause your system to oscillate. Here, it's basically a constant, a step of 4, which if you put it on the right-hand side, it will have the positive magnitude of 4. And so the only real difference is now, instead of putting in that cosine when you Laplace transform, this is now a minus 4 over s. So that v of s, if you go through the algebra, will be something like v of 0 minus over s plus 8 plus 4 over s plus 8. And now what's your structure for v of t? Plus what? Is that okay? That's what it is. You have a constant and a decaying exponential. And if I said, what's the final value of v of t in this particular problem, what would you tell me? It's k2, right? Not k9, so you don't have to worry about it being a dog, but it's k2. It's skis. Do they still make skis? K2 skis? Maybe I'm dating myself here. Used to be a company, I think, that made snow skis. Sorry. Long time ago, when I was your age. Maybe. It's hard to believe I was that young. Huh? Questions on that? That's the structure. Question. What if we now gave you a circuit and I said find v sub 0 of t for t greater than or equal to 0? And maybe the circuit is the following. Let's say it's now 8. Here's 6k, 2k, and here's a 125 nanofarad capacitor, and this is going to switch between these two locations at 0. And let's say this is 400 and this is was this a homework problem? No? Okay. I can't remember. Are you questioning my drawing? What? Which one? The 400 is supposed to be a resistor. You're hurting my feelings. So the 400 vertical is a resistor. To the left of the rightmost element is an inductor of 125 millihenries. Then I have a capacitor of 125 nanofarads. And now I want you to find, oh, yeah, V sub 0 of t for t greater than or equal to 0. Do you have an idea what to do? Okay, so first we probably need to find the initial conditions on the circuit elements. Right now, that switch is over on the left, and what's happening to the current through the inductor? And let's say that switch has been on the left for an infinite amount of time, and an infinite amount of time in electrical engineering could just be 5 time constants. When your time constant's 10 milliseconds, 50 milliseconds. But it's been there a long time. So maybe it's been there for a second. That's huge. So it's now been over here for a long time, and at t equals 0, we'll flip it over to the other location. But prior to t equals 0, I have an inductor in series essentially with a resistor, and that resistor is just going to bleed off any current in that inductor. So there will be no current flowing in that inductor at t equals 0 minus. And what's going to happen to that capacitor at t equals 0? Before t equals 0, what's happened? It's been in this position for a long time. We have a constant source. So it's just going to open up, isn't it? It's going to be an open circuit, and you'll simply have that 8 volts divided between the 6K and the 2K. And the voltage across that capacitor is going to be the voltage across that 2K ohm resistor, which is 2 over 2 plus 8 Ks times 8, right? Meaning, we can now start thinking about, well, this is, let's say, V sub C. After time 0, that's going to be V naught. Everything's going to be in parallel. And we also have, let's say, I sub L. But we now know from just thinking about this that we can find the initial conditions on the capacitors and the inductors. And the voltage on the capacitor is 2 volts by the voltage divider. That's simply 2K over 2K plus 6K times 8. That's where that's coming from. And I hopefully convinced you that the initial current on the inductor is 0. And now we have the initial conditions for what's going to happen to the circuit. And I would probably redraw the circuit since it looks a little complicated right now with all of those switches. I would say, okay, part B, let me redraw the circuit for time non-negative, and that's really just going to be the capacitor, the inductor, and the resistor. Sounds like a story, doesn't it? A bedtime story. The capacitor, the inductor, and the resistor. You guys should all just be feeling warm and fuzzy right now, maybe with some cookies and milk, right? This should just be saying, oh, this looks really good. This looks very comforting because this is a parallel RLC circuit. How many energy storage devices are there? 2. So you would expect what kind of an order for your circuit or your equation? Second order. And now we know that we want to write that in terms of this, let's say, voltage V naught. And what's going to drive that voltage? Our initial conditions. There's no source on this circuit after t equals 0. And now we could say, well, to analyze that, why don't I just write a KCL? I could think of this current, I sub C. I could think of this current, I sub L, and I could think of this current, I sub R. And ideally, I would find those in terms of V naught. Meaning from KCL, for t non-negative, I know that I sub C of t plus I sub L of t plus I sub R of t is equal to 0. And that should give you some points. Some, key word, 2 out of 100, right? You now know my partial credit scheme. But now you can gain some more points by writing down Eli and I's, right? Because you know that those govern the current voltage relationships of an inductor and a capacitor. Meaning, what is I sub C of t? So that's C dV dt, where V is the capacitor voltage. In this case, that's V naught. That's our output voltage. That's the voltage across all three. The next one that's easiest is I sub R. And that's Ohm's law. That's V naught of t over R. Which, if I just ask you to find the governing differential equations, you're almost there. You could say, wait a minute, I have an inductor, so let me use Eli. And Eli says that I sub L of t is equal to, no, let me do that. I can't spell, can I? It's too late in the day. I said Eli, Hal, which is V is equal to L di dt. So it needs to be V sub L is L di sub L dt. And there is, I know that this is the same as V sub 0 of t. So that I really have two equations that are first order that are coupled with this collection of equations. I can now write that first KCL relationship as C dV sub 0 dt plus I sub L of t plus V sub 0 of t over R is equal to 0. And the other one is simply the Eli equation. I have L di sub L dt is equal to V sub 0 of t. And that really would be the governing differential equations if that's all I ask for. for that circuit. And it's second order, isn't it? It's two coupled first order. I have a I sub L prime and I have a V naught prime. But if I'm asking you now for V naught of t, maybe you could Laplace transform these, solve this second equation for capital I sub L of s, and replace that in your first equation, which you're going to get an I sub L of s. You want me to do that to get a second order differential or a second order equation in the frequency domain for V naught, capital V naught of s? Let me do that, okay? If I wanted the time domain second order differential equation, then I would want an integral differential equation, because you would need to solve that second equation for I sub L, and that now involves an integral. Was that me? No, okay. Didn't know if that was my alarm and it was telling me I was out of juice physically. I need to be plugged in. Huh? You could, no, you could, so the question was, can I go the other way? Can you now rewrite the equation in terms of the inductor current? And you could. It's just that I was asking at the very beginning to find V naught of t, so I'm wanting to maybe write this in terms of the output voltage across those three elements. But you could rewrite that in terms of I sub L of t. And that might, well, yeah. So that would give you a second order, because now you would want to differentiate V naught of t to replace that dV naught of t dt, and that will give you an L d I sub L of twice. So you'll get a second order plus the I sub L, and then you'll have an L di dt there. Let's now Laplace transform these two equations. I have two equations. What happens when I Laplace transform the top one? C I don't need to worry about. That's a constant. V sub 0 of s minus V sub 0 of 0 minus plus I sub L of s plus V sub 0 of s over R is equal to 0. And what did we calculate for the initial condition on the capacitor voltage? That was 2. So we are going to be able to replace this with a 2, aren't we? A number. Then for the second equation, if we Laplace transform that, we have L times S, I sub L of S, minus I sub L of 0 minus, equaling V sub 0 of s. And what did we compute the inductor's current to be initially? That was 0. So that initial condition actually goes away. And from the second equation, from this expression, we can now solve that for capital I sub L of s. I sub L of s is now 1 over SL V naught of s. Which can be used to get rid of that I sub L of s there. Meaning, I now have C times S V naught of s minus 2 plus V naught of s over SL plus V naught of s over R is equal to 0. Questions on that? And where that came from? Yes or no? Now you can solve that for capital V naught of S, and you should end up with a second order denominator expression. And you could use the appropriate R, L, and C's that were given to give you a collection of, in this case, it actually ends up being two real unequal roots. And so you're going to get two exponentially decaying waveforms added together. Is that okay? Is that enough for now for that? You should be able to carry that on through with the appropriate values for R, L, and C and evaluate that expression for V naught of t, little v sub 0 of t. What if I gave you the following? I said, okay, here's another differential equation that I want you to Laplace transform. Suppose I now say that you have v double prime of t plus 4v of t is equal to e to the minus t minus 1 u of t minus 3. And maybe I give you that v of 0 minus is 1 volt, and the derivative of that voltage at time 0 is minus 1 volt per second. What's the hard, yes, question? So now the difficult part of this problem is really getting the argument in this exponential term on the right to be consistent with your unit step argument. When are you turning that on? I think that was the question, is that doesn't look right. And that's correct. It doesn't look right. And you need to somehow manipulate this exponential, this t minus 1, to look more like t minus 3, because that's what we're used to Laplace transforming, is e to the minus t u of t. We need those t's to be the same, or the argument of those t's. So let's look at that. That's really sort of the most, well, that's the biggest reason for this problem, actually, is so you can massage this to look like something that you can apply directly to your Laplace transform tables. And so you may need to use some operational transforms after you've done the algebra. Meaning, we're trying to now look at, let me change that. We want to look at e to the minus t minus 1 u of t minus 3. Can we rewrite that? And in particular, what I want to do is, I know the decay rate is minus 1t, right? From this. But I need in here to really have, right now that's what I have, but I really need a minus 3. But I can't just subtract a minus 2, but I can add 0 to anything. And that's what I've done. So that's equivalent to the left-hand side. Are we okay with that? What I now have that I want to sort of keep is that minus 1 and a minus 2. That will give me the minus 3 that I want. And the other piece is really just a scaling factor. That's an e to the minus 2. meaning I've now rewritten that left-hand side to be equal to e to the minus t minus 3 and an e to the minus 2, where this minus 2 is coming from that combination. And then this is u of t minus 3. This piece is now just a scaling factor. E to the minus 2, you can compute that, and that's just going to be a number. It's not very big. E to the minus 1 is it about 0.37? So you square that. So that's not very big. That's e to the minus 2. You know e to the minus 5 is less than 0.01, isn't it? So e to the minus 2 is between e to the minus 1 and e to the minus 5. It's e to the minus 1 squared. But it's a number. You can compute that. Somebody will do that for me on their calculator. What is e to the minus 2? .135. That's just a number, isn't it? 0.135. So that just moves around, and you can scale whatever you need by that, so that now we have, this is now 0.135 e to the minus t minus 3 u of t minus 3. And maybe you're not comfortable with that, but can you inverse Laplace transform, or I'm sorry, can you Laplace transform this? What's the Laplace transform of this expression? This should be automatic by Thursday, okay? If it's not now, you need to be very comfortable with this. This is just a decaying exponential, and you know the amount of decay. It's maybe indirectly there, but that's just 1. So this is now 1 over s plus 1. Is that okay? Now, if I wanted this instead of e to the minus t u of t, that's now a delay. So that if I'm looking to Laplace transform e to the minus t minus 3 u of t minus 3, I have this piece coming from e to the minus t u of t, but that's actually delayed by 3 units of time. And a delay is e to the minus delay times s. So this is now e to the minus 3s, and that's now the Laplace transform of that. And if you need to scale it, which you do, then you simply would multiply by that e to the minus 2, which is the 0.135. And now you have that most difficult part of this original differential equation. You have the right-hand side of Laplace transform. That's just a forcing function. And it's a forcing function that's an exponential decay, with the exponential decay rate being e to the minus t, and it's just started a little bit later. Pictorially, what are we doing? We really have, if you wanted to see, this might help. If I said sketch e to the minus t, you would start at 1. You would sketch it better than me, obviously, but this is now e to the minus t. But what are we doing? We're really only turning that on at 3. So at 3 is when we turn it on, and so this is now what we have. that's now that e to the minus quantity t minus 3 u of t minus 3. That blue piece. And we are Laplace transforming that. And what is that? That's really just a scaled version of e to the minus t. And that's where that e to the minus 2 came from. We turned it on at 3 by that u of t minus 3. Actually, I guess I didn't do it quite right, did I? Because we started initially with e to the minus quantity t minus 1, so I'm off a little bit. I should have started it at e to the minus t minus 1 instead of e to the minus t. But that's sort of the idea. It's not the correct answer, but it's the concept that I was trying to convey just then. Are there questions on that? What about maybe you did just go out and buy a calculator and you want to be able to use it on the exam, and maybe I give you some gift that says find little f of t given capital F of s, and there's capital F of s. What I would want you to do on the exam is, if you do have a calculator, you should say by calculator, and then write down capital F of s. And that, if it's the TI, you would be sort of using this expand command. And then you would write down 1 over s plus 1 plus 2 over s plus 3. Whoops. And the calculator would actually give you a minus, whoops, that was a 3 if you were looking, s plus 5. Is that what it gave you? And now you would simply say, okay, by calculator I get this capital F of s, and now you should all, once you have that capital F of s, you should be able to immediately say, that's e to the minus t plus 2 e to the minus 3t minus 3 e to the minus 5t u of t. Yes? That works for real roots, but I think if you do the expand with complex roots, it will give you the expansion using real coefficients. So you would now have the sine and cosine, or the exponentially damped sine and cosine, and you would have to keep track of those two pieces. That may or may not make sense, but we can talk about that later. Question? That works for the 89. It works for the Inspire. I don't know what else it works for. The Expand may only work for those calculators. Pardon? I don't think it's on the 84. So what I would do, especially if you're running short on time, you should be able to, by inspection, write down this middle structure and just say A over S plus 1 plus B over S plus 3 plus C over S plus 5. Write down the time domain equation and say, okay, if I have a little bit more time, I'll find the A, B, and C. But you could even set those up as an equation. You could say A is equal to. And these are just case 1, so those won't be that hard to solve for even that way. And sometimes you may feel more warm and fuzzy that way than trusting your calculator. You may say, let me find the A, the B, and the C and see if I'm okay. And maybe your calculator will verify your computations. Let's look at one maybe that we haven't yet looked at in terms of Laplace, inverse Laplace transforming. What if I gave you, we've sort of looked at this, maybe we have, but what if I give you that? and I say find, pardon? So now you can break it up into partial fractions, and let's see, I guess the calculator will do that, won't it? With repeated roots. If you use expand, I think the calculator will do that for repeated roots, but I was wanting to show you that if you don't have the calculator, you can find those roots, in this case, without really even having to have two coupled sets of equations. Meaning, what's the structure for capital F of S? You have A over S. So let's say B1 over S plus 1 quantity cubed. And now I'm going to just keep going with the B's, right? So I'll just keep going with those until I have my power of that factor, S plus 1 to the 1. And now I need to find my A's and the B's. But which of these A's and B's can I find using case 1? A and B1, right? So I can find A rather quickly. A is now going to be, I just multiply both sides through by S and let S equal 0. That's the value of S that causes the factor below A to vanish. That's where that 0 comes from. This now becomes 2 over 1. So A becomes 2. That's pretty quick. It's probably quicker than plugging it into your calculator. And we can find B1 as quick. That's now S plus 2. We've now multiplied both sides through by S plus 1 quantity cubed, so the only thing left in the denominator is the S. And at what value of S do I evaluate? Minus 1, which is the value of S that causes the S plus 1 factor to vanish. Now I have minus 1 plus 2 over minus 1, minus 1. Now, B2 and B3, I could pick two convenient values for S, and then I'm going to get two coupled equations. So I'm going to see, can I uncouple these and just have one equation and solve for B1 and a final equation and solve for, I'm sorry, one equation to solve for B sub 3 and another equation to solve for B sub 2. And I can do that by using different strategies. Did anyone use the limiting strategy where you multiply everything through by S and let S go to infinity? You didn't do that? Let's try that. So now for B sub 3, I'm going to use the limiting expression, meaning what I'm doing is I now have f of s, so I have s plus 2 over s times s plus 1 cubed, and I'm going to, well, and then I have a over s plus b1 over s plus 1 cubed plus b2 over s plus 1 squared plus b sub 3 over s plus 1. And now I'm going to multiply every term by s. And now take the limit as s goes to infinity. What do I have on the left-hand side? What are my highest powers of s? Or I could cancel those two s's out front in the numerator and denominator, and I now have s over s cubed. Or I have s squared over s to the fourth. And as s goes to infinity, what's that become? 1 over s squared, that's 0. So my left-hand side becomes 0. Is that clear what I'm doing? Now I'm taking the limit as s goes to infinity. If I apply that to the first term on the right, what does AS over S do when I let S go to infinity? Pardon? I just get A, don't I? The S's are moving in step with each other, top and bottom, and so now I just get an A. And I've already found A. That was 2. So, okay, I'm fine. If A's still in my equation, I'm okay. Now, the next term, what happens when I let S go to infinity? I have S over S cubed, or something over S squared. That goes to 0. What about the B2 term? S over S squared, that's 1 over S. As S goes to infinity, that likewise is 0. What's the last term? I just get B3S over S as S goes to infinity. So the S's are going at the same rate. That just gives me B3. Are you okay with that expression? Now I have one equation. I already know what A was. That was 2. So this now allows me to very quickly find B3 is minus 2. And I can now find B2 by a convenient value of S. And it's now the only thing left to find, so I just have one equation and one unknown. So B sub 2, I'm going to say, oh, a convenient value of S. And for me, let me just say, let me use S equal to 1. So that now I had S plus 2, so 1 plus 2 over S times S plus 1 cubed equaling A over S. Is that true? Was just over S, wasn't it? Plus B1 over S plus 1 cubed plus B sub 2 over S plus 1 squared plus B sub 3 over S plus 1, where I'm replacing S everywhere with 1. And I know that A was 2. What else have I found? B1 was minus 1. B3 I found to be minus 2. Ooh, you know what? I don't know how long we have this classroom. I thought it was, I don't know. Anyway, they're not used to somebody being in here. We may get kicked out. Is it clear now? The only thing left to do is solve for B sub 2. And it's not too difficult. So that now I have my partial fraction expansion. I now have capital F of S. Who knows what I have? I had A, which was 2 over S, plus B1, which was minus 1 over S plus 1 cubed, plus B sub 2, which I just found to be minus 2 over S plus 1 squared, plus B sub 3, which was minus 2 over S plus 1. And F of t now becomes 2. That's the constant. And then I have minus, actually that S plus 1 cubed, I have a 1/2 times whatever it was, t squared e to the minus t. Then I have a minus 2t e to the minus t minus 2 e to, I have too many minus 2's, but that's just the way it ends up. That's now my little f of t. Yes, question. The 1/2 comes from the transform pair, and you'll have to either find that in your book or derive it. But when you have something cubed, now you have a 1 over basically 3 minus 1 factorial. And that's where that 1/2 is coming from. So that's coming from the transform tables. This 1/2 didn't come from the minus 1, did it? The minus 1 is scaled by 1/2. That's because we have this s plus 1 quantity cubed. Yes?
Is there any occasions where the limiting expression technique will not work?
Where the limiting expression technique won't work. So are there times when that won't work? The reason it works is because the partial fraction expansion is true for all values of s. So it may give you redundant information, but it should always work. Am I hearing things? Now I'm really sensitive to somebody coming in. Ooh. Questions? Did that answer your question? So it may give you an equation that basically repeats or reproduces information you've already obtained, but you can use it. But the reason why it was nice here is because it allowed us to find b sub 3 as a single equation in one unknown b sub 3. The b1 and the b2 were eliminated. And we could sort of see that in anticipation of applying the limiting case because we know we have an s cubed and an s squared downstairs in those two pieces. And we'll only have an s upstairs. Are there other questions? I mean, we could go all night, I guess, but you may want to get home and do something else. Study. Questions? Yes. I'm not quite sure what you're asking. The ladder step function or the ladder technique for finding the circuit equations, the governing dynamic equations using the ladder technique? Okay. But I do have an example that was somewhat, did I talk about the ladder technique tonight? No. So if I ask you to find the governing differential equations for the following, maybe I said, and this might be on an old practice exam, if I now ask you to find the equations that govern this circuit, call that R sub 2 and this is R sub 1. You could use the ladder technique to find this. But in terms of what variables do you probably want to be using to write your equations? The capacitor voltage and the inductor current. So now you would put those into your circuit and you would try to work your way back to the source. Meaning this capacitor voltage is going to start appearing everywhere because you know the current voltage relationship via ice. You now know this capacitor current is C dV sub C dt. So now you have the current through this resistor, and you can now find the voltage. This voltage is now R1 I sub C. And I sub C is C dV sub C dt. You now know this voltage. You now know this voltage from here to there. So here's your reference node, the bottom line, because you know this voltage is just V sub C, and you just calculated this voltage drop across R1, and you can start working your way back. And once you have the voltage I'm pointing, nobody on listening to this knows what I'm pointing at, do they? But now that we now know this voltage, if we called that V sub 2. And once we have V sub 2, we can get this current. And once we have that current, we can write those two currents in terms of I sub L. And we know via Eli that we have this voltage. And now we're back to V. Meaning, if I do this really, really fast, here is V sub C, and we're trying to write these equations in terms of I sub L and V sub C. We know that I sub C, which is right here, is C V sub C prime. V1, though, is now R1 I sub C, which is R1 C V sub C prime. V sub 2 is V sub C plus V sub 1. And we now have that in terms of V sub C and its derivatives. This is now V sub C plus R1C V sub C prime. And now we can get I sub R sub 2. Is this making sense? So we're working our way back to the source from the right-hand side in terms of effectively the capacitor voltage and the inductor currents. Are you comfortable continuing? You now need to find I sub R sub 2, which is just this V sub 2 divided by R sub 2. Now you know all of the, you can apply KCL right at that V sub 2 node. I sub L is equal to I sub R sub 2 plus I sub C. Once you have I sub L, you can use Eli to get V sub L. And once you have V sub L, you can do KVL around the big outer loop and say I have minus V plus V sub L plus V sub C plus V sub 1, and you have all of those in terms of your known expressions. And now that's your governing differential equation using the ladder technique. But I've solved this, I think, many, many different ways on that practice exam. If that doesn't make you feel good, that analysis, you could do this many other ways. Yes? So all of the boxed answers on these practice exams are acceptable answers. The question was, which of these which of these answers is the preferred answer? There really isn't. So a lot of times your eyes may get rolled back in your head and you're going, why is he doing this so many different ways? Well, it's maybe that one of those ways might be more acceptable to you as an approach to solve it, but they're all equivalent. So if you do it one of those ways on the exam, you should get credit for it. Should meaning if I haven't fallen asleep while I'm grading it and I go, I don't know what he's doing. But you should get credit. They're all equivalent answers. Other questions? Thank you for your patience and your duration on this, but I hope this was helpful. But you guys really do have a lot now in your toolbox of kit of skills.